Afternoon, good evening to everyone. I am Maria Luisa Toledo from IBGE, and I'm the leader of the United Nations Regional Hub for Big Data in Brazil. It's a pleasure to welcome you to the fourth webinar in our series on climate change indicators. Throughout this series, we'll be hearing from experts who will share valuable insights on utilizing new data sources and technologies in climate change mitigation. We are honored to have with us our speaker, Dr. Ryan Vargas Mareto, Assistant Professor at the Faculty of Geoinformation Science and Earth Observation of the University of Twente, the Netherlands. Professor Mareto is a Brazilian. He received the bachelor degree in computer science from the Federal University of Ouro Preto in Brazil, and a master degree in remote sensing and PhD degree in applied computing from the Brazilian National Institute for Space Research, the INPE. With a background in computer science and remote sensing, his main expertise is the application of deep learning, machine learning, data mining, and other pattern recognition methods to geospatial data. Professor Ryan, thank you very much for accepting our invitation and for making time to share your expertise with us. We know you have a busy schedule, so thank you. And the floor is yours.
Thank you very much, Maria Luisa. Can everyone hear me well? Is it okay?
Yes,
Yeah.
it's perfect.
Okay, thank you very much. So today I'll talk a little bit for you about the research we have developed here on using AI and mostly deep learning for mapping several aspects of the world. So we have developed some applications on mapping forests, estimating biomass, mapping urban spaces, and so on. I had put here before a slide presenting myself, but Maria Luisa already made an introduction. Thank you very much, Maria Luisa. So basically, as she said, I'm Ryan Mareto from Brazil. I'm assistant professor here at the University of Twente at RTC. And I have worked mostly with deep learning for combining different types of remote sensing data and for mapping several aspects on the environment and social applications. So basically, first to understand why do we need machine learning and what is that? Every year we have had new sensors being freely distributed, a lot of data arriving, new satellites, new airborne sensors, and so on. And with a lot of not only a lot of data, but a lot of complementary data with different types and different characteristics, different resolution, different scales, and so on. In one hand, with with that amount of data, and we have also dozens of terabytes being generated every day. That on one hand, that has opened a great opportunity to understand the world from the local scale to the large scale on the continental country scale or even on a world scale. But it also brings a big challenge on how can we properly deal with such amount of data. So with that, the traditional manual and visual interpretation approaches, they become unfeasible, especially when you go for the large scale. And together with that, we have all the time an increasing demand for extracting useful information from this data. One example is the Sustainable Development Goals from the United Nations, where we have several different domains of applications that have been stimulated for the countries for development. and for sustainable development. And we need to properly measure all those indicators in a way that we can understand how each country, how each region is evolving on these goals. Other examples are like with the increasing impact of the climate changes, where we have to measure and understand what's happening to mitigate that, monitor biodiversity that in a lot of regions is under pressure and under a lot of problems. Also, to inform and enable regulatory policies. For example, we have also here a project on monitoring oil spills. There is also a lot of application for that on smart cities and so on. So this brings us to what we have called the AI era, where we have now, with the increasing capacity of the machine learning and deep learning algorithms, together with the increasing computational power with cloud computing and high performance computers with powerful GPUs and so on, that had opened an unprecedented opportunity to perform large scale analysis and to better understand our world. But then we have to understand what is this monster machine learning, what is this monster of artificial intelligence that we are talking about. And for that, we need to think first, how do we learn? As humans, we learn from past experiences, from things we see, from things people tell us, that we learn in school, and so on. Then, machines, on the other hand, computers learn from not learn, they follow instructions that we humans give to them with through programming, mathematical functions, logical functions, and so on. Then, back in the 40s and 50s, started a field in computer science that started with the question, what if we could train the computers to learn from past data? We could then make the computer execute tasks that we humans do in a much faster and much more efficient way. Open space for using our capacity as humans for more complex analysis on the information that is extracted from that data, for example. So the artificial intelligence, therefore, is a field from computer science that focuses on developing machines and algorithms that are able to perform automatically without the human intervention tasks that are usually performed by humans. So it's also focused on making the machines learn by themselves. And one of the requirements is that we could do that without or with minimum human intervention. And inside that big field, there is a field that we call machine learning that is focused on the learning process of that, because artificial intelligence involves also robotics and several other components that are also focused on the taking actions. And the machine learning is more focused on extracting information. And inside the machine learning, there are fields focused on representing the knowledge. And inside that, there is what we call deep learning. Those are machine learning algorithms that are much more complex and focused on extracting also some abstract features from the data without the need of the human to design those features. That's in the shallow, what we call shallow machine learning. That is the traditional machine learning. We need a big effort in what we call the feature engineering, that is developing how we will represent that knowledge. And the big advantage that comes with deep learning is that the model learns also the knowledge representation by itself. So this was a very quick and very shallow introduction of about just to contextualize what we are talking about. And some applications of AI and machine learning are in autonomous vehicles, smart cities, You will see that a lot in games. That has been used a lot also in economy now for analyzing stocks, for trading, and so on. And of course, for automatic mapping and information generation from geospatial data. That is our focus here at ITC. So the first application that I will show for you is an application that we developed in the past 2 years in collaboration with ITA in Brazil. We received Dr. Paulo Silva Filho. He defended his PhD in the end of the year, and I had the pleasure of being one of the supervisors together with Professor Cláudio Percelo and Professor Renato Machado. And basically, the idea of his work, he worked actually in two fronts. The other one I will show later as well. One was on mapping vegetation in the Brazilian Cerrado, and the other one was on mapping informal settlements, mapping slums that we call in Brazil favelas, and but mostly focusing on fusing different types of data, SAR, optical, and some auxiliary data as well. So this is a paper that was published in ISPRS, Journal of Photogrammetry and Remote Sensing, in the end of last year as well. And basically the idea here was to combine different types of data to produce automatic maps from the nature of vegetation in the Brazilian Cerrado. Why the Cerrado? The Cerrado is the second largest biome in Brazil. More than 50% of the biome now have been already converted for anthropic uses, and it have had a strong expansion of agriculture and livestock in the past years. It has been one of the biggest uh, expansion of deforestation and suppression of natural vegetation in Brazil in the past years. And only 80% of the biome is protected by conservation units. So another reason is because the Cerrado is one of, if not the most complex biome in Brazil, where you will find several different types of vegetation formations with forest formations, savanna, grasslands, uh, other types of, and these big areas, the grasslands, savannas, and forests, these big classes, they divide in almost 30 different classes as well. So, which brings us a lot of complexity to really prove the potential of the algorithms. So we selected basically 10 areas spread across the whole biome and across the different ecoregions in the biome. And the idea here was to combine Sentinel-1 and Sentinel-2 in 10 meters resolution to map the anthropic areas and the nature of vegetation. And then we combined the ground truths from Terra class, some classes from map biomes as well, but mostly we got from Terra class, and also from the vegetation map produced in the FIP Cerrado program by INPE. Then we combined that to produce our ground truth, and we divided our ground truth in two different levels of classes. The first with 3 classes only, and the second with 7 classes in a second level. And another layer of complexity here in this application was that we were dealing with images on 10 meters spatial resolution and trying to produce maps on 10 meters, but our reference is on 30 meters, which brings one more layer of uncertainty over on top of the whole complexity of the application. Then we developed here two different networks, 2 levels of networks. One, actually, that these networks were combined for producing a hierarchical classification where the network would classify first in the first hierarchical level, and then in the second one, spreading the 7 classes. So Here is a representation of the network that combines Sentinel-1 and 2. And here, some of the innovations here was the two producing that with two outputs, one in 10 meters, the other in 30 meters. And the idea is that since our reference is in 30 meters is where we have the lowest uncertainty, we used that with two different loss functions where we would uh, do an optimization in 30 meters and then fine tune that in 10 meters, of course, keeping in mind the uncertainties that the 10 meters brings, especially on the border of the objects. And then Paulo tested several different architectures with early fusion, middle fusion, and also late fusion. Sorry, and also late fusion. And then also testing some feature adaptation that were combining better the features of both images. Sorry, I'm coughing a little bit today. So then we have two different types of feature adaptations here. The first one based on convolutional blocks that would get the two images and extract features of the two types of data together. And the second one based on wavelet multiscale decomposition that would also do this combination in another way. So another, and I think what was the biggest innovation of Paulo's work was the way he quantified the uncertainty and the way he calibrated this uncertainty to reflect the the confidence of the model. So the idea here is that by using Monte Carlo dropout with the MCLU, that is the multi-class label uncertainty, we uh, we generated some diagrams with that, and then we calibrated that uncertainty that was coming from the maps with the confidence of the model, inserting that uncertainty as part of the loss function. The main advantage of that is that we generate models that we have called uncertainty aware models that together with the map they produce a map of uncertainty where you can highlight the main areas of attention, and then we can focus because most of the maps, all the maps produced by machine learning and deep learning, they need to have an audition by experts later to ensure the quality and to understand where the map is wrong and where it's correct. And then here, with these uncertainty maps calibrated with the output of the model, we managed to make these auditions focused where we know that the model has a higher uncertainty and a lower confidence. So how that was done by first analyzing and calibrating the distribution of that uncertainty, and then defining some thresholds on that where the incorrect where we would have the incorrect uncertain and correct uncertain and the four different layers here of uncertainty, and we could generate some maps focusing where we would highlight the areas of attention. So here examples of how that was done. We have here the uncertainty before the calibration, after the calibration, and the maps that were generated, where we have here the darkest it is, the more uncertain, the lighter it is the color, the lower is the uncertainty. And then we could see that some of those areas here in dark are the areas that we can send later for the interpreter to do the analysis and to understand what are the problems so we could maybe improve reference or improve the model in those areas or even improving the map if it is in a production environment. So here, some examples of the results. In the first part here, the areas of attention highlighted by the models. And one interesting thing is that really matched quite well with the areas where the model was having mistakes. And here, some of the results with where we have here the reference, the Sentinel-2 images, and then the inference in the level 1 in the first 3 classes, in level 2 in the 7 classes. So here some comparison also from this algorithm with the state of the art. And the state of the art in this case, we considered the model from Kennedy et al. From 2022. That was the best model that we had found with for this type of application. And we could see here in bold the areas where our model performed better than their model. Also, we performed the comparison of several different loss functions, with some of them considering the uncertainty, some of them not considering the uncertainty, and also different types of loss functions based on cross entropy, the focal loss, dual focal loss, and so on. So here is the calibrated focal loss, and here is the calibrated dual focal loss, where we inserted the uncertainty. And we could see here that in most of the cases, when we calibrate that, the model tends to perform better than when we don't calibrate the uncertainty. So another ablation study here with the different hierarchical model, and we have here highlighted also where the model performed better. In most of the cases, in the hierarchical model, the model tend to perform better than when we consider only one model for everything instead of splitting hierarchically the classification. So of course, as like any other model, this has some limitations. One of the limitations come from when you insert the uncertainty in the loss, you fall in the risk of generating some bias with the model learning better. Also, where you have more uncertainty, and especially if you have uncertainty in your label, this may be a problem. But in our case, we could see that this also improved quite a lot the data and improved quite a lot the results. And also with the advantage of having the guided audition later when you need to perform audition and quality assessment of your maps. So another project that I will present for you is a project that is called ID Atlas. That is a project that we have developed in the past 2 years, founded by the European Space Agency. That focuses mostly on using artificial intelligence for mapping slums, mapping what we call the private areas or informal settlements. And this is our team, and the two wizards behind the code are Pedro and Paulo. They are who developed the model under our supervision, and also with each one of us working other different aspects as well. And here, these three on the corner are our advisory board that they have helped on steering the project and steering the directions of the project. So basically, ID Atlas is part of another bigger network of projects that's called the Idea Maps ecosystem. That is a big research network focused on mapping different levels of urban deprivation and the different aspects of the urban deprivation. So In ID Atlas, we have focused on mapping 8 different cities spread across the globe. And the idea here was to select cities in different continents, but also cities that have different types of deprivation and different types of urban morphology. So we could move a bit forward in the direction of developing a worldwide model where we could map the whole world. And this project is coming to an end now, and we are now in the phase of trying to acquire more funds for a follow-up. We already are in the phase of negotiation for another project for mapping the whole extent of Argentina, and we are also applying for several different other grants uh, for mapping other areas and also scaling up for other continents and also for moving towards a global model. So basically, the whole project have been developed on cloud computing using the CryoGeas system, that is the cloud computing from the European Commission and from the European Space Agency that are provided by several companies under the founding of these institutions. So the idea is that by mapping the different aspects of urban deprivation, we can improve the reporting of SDG 1111 that is focused on the proportion of urban population living in the private areas. And the idea is focusing here on not costly, but in a very cost efficient approach. Because if you do that in household surveys that are the main methods nowadays, this is quite costly and you have quite a low frequency. It's very hard to update your maps every year or even with a higher frequency. By using free Earth observation data and artificial intelligence, we produce maps that are scalable, affordable, and we can provide a high temporal resolution for that. So basically, we have developed that by combining mostly Sentinel-1 and Sentinel-2 with some auxiliary data, but we have explored also the planet scope from the Norwegian government program that is provided for free. We have explored also world view and other very high resolution images. And we have developed that on what we have called a user-centered design process, a user-centered approach, where we have frequent meetings and frequent interactions with the local communities, with the local stakeholders from each of the 8 cities to improve our reference, but also to understand which type of data we need to provide them to be more effective on answering to their needs. Because in the end, our main goal is that our maps could be used for developing public policies for the communities to request their rights or any kinds of for NGOs that are willing to improve the living conditions. So then the main idea of the project is to produce 3 levels of data. The first one is a binary map, but multi-temporal map, focused on mapping the dynamics of the slums from 2019 to 2023 across the 8 cities. The second one is to produce what we call the slum severity or a deprivation index. And the third one is the indicators on a city scale that is focused on really the SDG informing, where you can measure the proportion of population living in each of these deprived areas and classify that according to the levels of deprivation. So some of the main challenges are first, mapping the urban space is quite complex, and the definitions of what is a deprived area, what is a slum, that varies a lot, not only inside the same country, not only across the globe, but sometimes even inside the same city. You have several different types of slums, you have several different types of the private areas. The resolution of Sentinel images, that is 10 meters, and not always gives us enough detail for mapping those areas. And also another problem is the quality of the reference data, that the first interactions that we did, the data that we had was not so accurate because those are mostly data that are not produced with the goal of mapping slums. So because of that, we had performed, and I'll show you in a bit how, we had performed several interactions with the users on improving this data. And here it's an example where we have in Jakarta, we had some polygons that were like this whole polygon defined as a slum, but the actual slum was only this part. And we had that in many areas because, for example, in Brazil, the data that we have comes from the census of IBGE, and then the minimum area of the census is the census district. The problem that that brings is that the census districts, they are developed for operational purposes. That is the area that a surveyor can do in a certain period of time. And with that, you have some areas, some polygons that they have both deprived and non-deprived areas in the same polygon and several things. But also, uh, defining like what is this threshold? How do we define what is a slum, what is a deprived area? Is something that there is no consensus in the community. There is no consensus even sometimes inside the same city. In the workshops that we did with local stakeholders, sometimes there were very long discussions on if an area could be considered as deprived or not, because this is also not so straightforward. And also, in many cases, there are some areas that through by looking to the image, you cannot say that that area is deprived, but when you go on the field, you see that that presents characteristics of deprivation. So here, example of what I told about the resolution of the images. Here we have one image, a world view image with 0.5 meter spatial resolution. And here on the side, the same area with a Sentinel image with 10 meters spatial resolution. And you can see that the level of details is not so big. And then we have some tricks to overcome that. So because of that problems in the data quality, we developed in collaboration with Giovili, that was a company that supported us in this development. This user data portal, if you want, just you can access through this link, you will see there our data. The data that is public is on 100 meters resolution, just to protect the privacy of the communities. This was a requirement that we had from several cities, that in many cities they have a lot of occurrences of evictions in those areas. So because of that, we cannot share publicly the exact location. We map that on a 100 meters grid, and then we share that public, and the detailed maps we share only with selected users that will not generate problems for the communities. So here, this portal was developed for so the users could go there, inspect. Here you can see in red our prediction and in yellow our reference. This is for the city of Medellin. And the idea is that the users can go there and check and correct our reference, but also correct our maps. So they share with us these polygons through the portal, and then we improved our reference and rerun the model, retrained the model, and with that we managed to increase a lot our accuracy for that. So here another example of in a higher in a zoom in from the portal. showing a bit of our maps, and this is for an area in Salvador as well. So, talking about the models, we developed three variations of the model. One of them, that is the one that has performed better, was a combination that used the Sentinel-2 in combination with building density extracted from building footprint. I'll show you in a bit what I'm talking about when I talk about this density. And so basically, the idea is that we have an early fusion block that combines the Sentinel-1, the Sentinel-2, sorry, with the density, and that throws into the network. Another one is we have called those multi-branch variations of the UNet of CNN. Another one that we tested was including SAR, Sentinel-1, Sentinel-2, and some ancillary data as well. And the other one was actually, this is the one that I told that performance. No, this is the third version. Sorry, the first one is the one that performs better. This second one, actually, we enter only with the image. Here, we updated that, but I forgot to update the slide. The third version is we enter with the image, and the density enters here in the loss function. So basically, the idea is that we trained the model to first learn how to estimate the density from the Sentinel images. And then instead of using a pre-computed density, we used this estimated density, extracting some more features and producing the classification of that. You may argue, but okay, why do you want to estimate a density from the image if you have that from the building footprint that is much more detailed? The reason is the building footprints, they are they are not frequently updated, so we have access to that for 1 year only. So if we make our method fully dependent on the density pre-computed from that, we lose a lot in the temporal transferability. So we lose a bit, and we want to produce multi-temporal maps to follow the dynamics of those areas. So because of that, we developed this model that estimates first the density and then use that there. And this model performed very, very closely to the model with the pre-computed density, showing us that like estimating the density is very viable, is very feasible for that. And the density, what I told you is like this. We get the Google building footprint is produced from very high resolution images with half meter of spatial resolution. With that, we compute in a 10 meters spatial resolution what is the building density in each of these areas, and we spatialize that as a feature that enters for the network. And here, another example of the reference data, also for Medellin. And when creating the data set, we split each of the cities in patches of 128 by 128 pixels, and those were split for training, test, and validation, where the training and test are used for training and fine-tuning the model, and we use the validation later to compute the accuracies where the model, in areas where the model didn't see during the training. Here are some examples. These actually are a bit older examples, but are the examples that we have comparing Worldview and Sentinel. The higher resolution of Worldview, and despite the numbers in Worldview were, as expected, much higher, we could see in the Sentinel that the overall pattern of the settlements was much better captured and was better mapped, reducing the noise as well. Here, some numeric results showing showing the results in the first version of the reference and in the second version of the reference. And another thing, just by improving the reference, we could also improve a lot our numerical results. And there were some cities here, like Jakarta and Mexico City, that these are the accuracy metrics only for the class informal settlements. And in those cities, we have two problems. First, we still have quite a lot of problems with the data, even after rounds of interaction with the users in these three cities here. And the second problem is that those are the most complex cities where you see the least difference among formal and informal settlement. And also, despite this, I didn't manage to include because this is a table that we produced this week only. But I have also we compared the overall accuracy of everything, and for all the classes, when you compare all of them, the accuracy is above 85, 90%, which shows that the model is learning very well. Just in some regions that the class informal settlement is not so well classified because of quality issues of the data set, the training data set, and also because of the complexity of the cities. Here, examples of the multi-temporal maps that we produced for Medellin. And here, a very interesting example for Nairobi, where we could find two opposite examples. One of a settlement that grew from 2019 to 2022, and another one. This was a settlement that we identified that it disappeared from our maps, and then when we checked with our local co-anchors there, our local stakeholders, this is a settlement that suffered from with an eviction in this period, and then that's why the settlement disappeared. So here are some examples of the deprivation levels across three cities. Here it is Medellin, this is Nairobi, and this is for Salvador from the left to right. And here another very interesting case from this project was that that happened not only in Buenos Aires, but the most relevant was in Buenos Aires, that there were several, during the interactions with the stakeholders, we identified several settlements that we were mapping thinking they were false positives, that were a mistake by our model. And in the end, when our stakeholders came to the field, these were actually new settlements that had appeared, and this helped them to improve their database. And this, especially for Argentina, is quite critical because they have a national database of informal settlements, where if a settlement is registered there, they cannot, by law, suffer eviction. And then this helped us to update their database, and that's why one of the main focus now is to scaling up for the whole Argentina as well. We have worked together with them so we can combine their expertise in the field with our maps, with our AI methods to improve their database as well. And this was interesting that even reached the international news in El País and also in national news in Argentina, the cases of where we managed to help them on improving their data. And the last application that I want to show you, I'll try to be quick here because I'm already running out of time. Sorry for that. So this was a paper that we developed in collaboration with Solvit. This was actually led by a company in Brazil called Solvit through Luis Cortinhas, who is about to defend his PhD, and Dr. Cesar Diniz. Luis spent 6 months here at UT under my supervision and the supervision of Professor Claudio Percelo as well. And he is about to defend his PhD, and this is the main paper of his PhD, where we produced maps of illegal mining that we call garimpo in Brazil, that actually Not necessarily a garimpo is illegal, but most of the garimpos, they are illegal nowadays. And then we managed to map the whole mining in the whole Brazil, separating the industrial ones and the ones with explicit signs of illegality. So here is an example of an industrial mining, and you will see the difference when it is a garimpo. Usually it looks like this. And garimpo was traditionally called artisanal mining. But if you look nowadays, the way they do that, it's highly mechanized and it's in a high scale. This cannot be called artisanal anymore. We propose it here also to call that mechanized mining, not only artisanal mining anymore because of these characteristics. And so the idea was we developed a lighter version of the UNet that was able to process that in a large scale. Here it's another example of a big area of garimpo in the Amazon. And the Amazon is the region that suffers the most with those illegal mining, especially because that have also some big environmental and healthy impacts for the population. So the idea is behind here again is when we are working with deep learning, we are not working only on the temporal and on the spectral domain anymore. We are assessing the whole contextual aspect of the image. And here some examples. When you get some examples of pixels of water that is affected by garimpo and water that is not affected, in several cases, you cannot identify spectrally the difference among that. But when you come for the spatial patterns as well, you can identify that much better. So this is an example of how this is the original UNet. And basically what we developed was a lighter version, reducing the amount of layers on that. Here, it's an example of a garimpo, a quite big one, in Rio Grande do Norte. And in a Landsat image, we used mostly Landsat images for this project. And here, the map, the classification that we produced from that area. So here is where the garimpo is located. So, and then we found some very interesting findings in this paper, and this paper was actually even published in Nature Communications that highlights also how big was the findings that we found there. And that comes mostly from the spatial analysis, where we analyzed it from 1985 until 2022. So basically, this is the map of the mining areas for the whole Brazil, where the garimpo has expanded only in 2022 around 35,000 of hectares. That is equivalent to the whole Atlanta in the United States. And also in 2022, around 92% of that the garimpo areas were inside the Amazon biome. And also here you can see some of the biggest frontier of expansion on that are in the Pará state. So, and this is one of the most interesting graphs that I would like to show here. That is, if you analyze from 2000, between 2018 and 2019, the total area of garimpo already overpassed the total area of industrial mining in the country. And also, if you see here, starting from more or less 2009, 2010, and having an accentuated increase here, we have almost an exponential increase of that. And when you look to that, especially under the protected areas, here in the indigenous lands, we had from 2016 and on also an exponential growing of these areas, and also inside the conservation units. So the main types of conservation units we have, especially in the Amazons, are the protected areas and the indigenous lands that are also focused on protecting the environmental areas. And these were some very interesting things that we found when we mapped this whole period on that. But then you may be questioning, how did we consider if we have signs of illegality or not? Basically, there were three things that we considered. If the garimpo is inside restricted areas, conservation units or indigenous lands or other types of protected areas, if there is an inappropriate permit or a lack of permit, because this whole data of the permits, it's public from the national agency that regulates that. So if the data falls in one of these three categories, we consider that as with explicit signs of illegality. And also, only in 2022, 15% of these garimpo have occurred inside restricted areas, which is a lot. And this is only a small fraction of the problem. When you look to that, we have 58% with inappropriate permits, 4% with lack of permits, which leads us to around 77% of explicit signs of illegality. And also, if you look to the temporal persistency of that, more or less, more than 40% was open in the last 5 years, and a lot also that were open inside these areas of the indigenous lands or protected areas, they persisted over time, which means there is also a lack of action on combating that. So here also we highlight the new frontiers of expansion of garimpos, and I will show you here very quickly also how we assessed the error on that. So basically, we split the country in in this grid of assessment, and we generated randomly 52,000 points that were one by one validated by experts in the field, remote sensing experts and experts in mining. And with that, we generated a gridded accuracy metrics for the whole country. So we have for every one of this grid, we have the accuracy that our map performed. So we are also using that to further improve that. And this is another project also that Luis is coming to the end of his PhD. So we are now in the phase together with Solvid and together with the guys of Map Biomas. We are in the phase of trying to get grants to get some fundings to continue that. And our dream is that we manage to develop a near real-time illegal mining detection system. So some findings here as well, that most of the garimpos that we found are that have signs of illegality. It is expanding very fast. It is really huge, heavily mechanized, and it seems very largely founded. So we cannot have all those characteristics and call that artisanal small scale mining anymore. And just some quick things. I think these I can skip because there's the last application that is some also. This is a work from a master student that worked with me last year, and she developed also a method for combining LiDAR, SAR, and optical images for estimating above ground biomass. And basically, we got around, I think, 21 or 22 of these big areas in the whole Amazon, and produced using some data that we acquired from INPE. We produced some maps of above ground biomass, And the idea here is most of the estimation of above ground biomass nowadays rely on field inspection. They go there, they measure the trees and so on. And by using satellite LiDAR, SAR, and optical, we can do that on a large scale and and perform that, also updating the biomass maps every year, so we can also produce better estimation of the carbon emission, carbon stocks, and so on. And here some examples of those maps. Our reference was a reference from a paper from Nature, from Jean Ometo from INPE, and it's the most accurate biomass map that we have for the Amazon nowadays. And we can see that in several areas, and one of the interesting findings here, if you look, for example, in this area, there is a river in the image that because their map is on 250 meters, and we managed to produce ours in 150 meters because of the higher scale of the images. And in areas like this river, we could get more details on that biomass estimation, and that indicates that our maps managed to get from a lower scale to a higher scale in a very good way as well. And also, besides that, we have developed several other approaches here on fusing SAR, optical, and other data for mapping deforestation, for mapping natural vegetation, detecting illegal vessels, and several other things like that. And I'll come here to the conclusion because I already passed too much the time. So some of the main challenges we have nowadays, first, is the lack of quality and quantity in the data sets. So we have not, for remote sensing, still we don't have that much data sets available nowadays. And this configures a problem because to evolve these algorithms for a data that has such a specific characteristics like remote sensing data, we need a big amount of data available so we can stimulate the community to develop those methods. But also another problem is besides the quantity, is the quality of the samples. Quite often, when developing models in remote sensing, we have sometimes, for example, a land use land cover map for the whole country for a certain year. But that map is a photo, let's say, like it's an image from an entire year, and it is usually produced with images collected in several different parts of the year because of cloud conditions, atmospheric conditions, and so on. When you have to produce maps with AI, you need to select the best images, and not always they will match with the map because the landscape is dynamic and that changes. Besides that, for as example, the case of the slums, we don't have so much accurate data available for many countries. So because of that, one of the biggest trends nowadays in the community has been what we have called the data-centric AI. And I still believe that this is one of the main frontiers that we have to evolve. And together with that, for large scale model, there have appeared nowadays the foundation models that are based on the large language models like GPTs and so on. But I would say one of the main challenges that we have nowadays for improving the quality of mapping with AI, of improving the application of AI in remote sensing, is focused on the quality of the data and how we measure this uncertainty and the quality of that with data that has intrinsically a lot of uncertainty as well. So sorry for rushing a little bit in the end, but I was a bit nervous that the time was quite much over the limit already. So thank you very much for your attention. I hope I managed to give you some interesting information today.
Thank you very much, Ryan. Great presentation. Thank you for sharing this so comprehensive perspective on the advancement in the area. We have some a lot of questions actually in the chat.
Oh, let me
I
see
believe
here.
we can I read some of them? I think
Yeah,
we it's already midday, but we can like take time to answer some of them. Um, let me see. People saying congratulations for the event, very relevant theme. Good morning. A specific question. It was in the beginning of the presentation, probably based on the first study case. Does the combination of data from Sentinel-1 and Sentinel-2 consider the same data collection dates?
uh, actually, we always try to get the closest possible. The same collection dates is usually almost impossible because the two satellites have even different temporal resolution. Sentinel-1 has, because both of them are constellation of two satellites, and now there is a new constellation that just came out, but I don't remember if it is already available. But basically, considering Sentinel-1 A and B, we have no Sentinel-2 A and B. We have a 5 days of temporal resolution because it's 10 day each, but they they are interleaving. And Sentinel-1 is 6 days because it's 12 days each of the satellites. And after, I think, 2020, Sentinel-1B had a problem. So we have only 12 days after that. So because of the problem with one of the satellites. But then what we try to do, we always try to get the closest date possible. And of course, we know that that brings some uncertainty in some areas, but it's the best you can get with different types of data.
Okay, thank you. People are like asking for the presentation. If you can share the presentation, maybe if you feel comfortable to share, you can send us and we like can make it available. But they were asking specifically for the name of the papers, but some
Mm-hmm.
of other participants found the links and shared.
Okay.
I think they were interested in the articles, the papers. Another question, how do you create the labels that match those satellite images? It was maybe in the second application you
Mm-hmm.
presented.
You mean for the slums?
Yes, probably. Yes.
Yeah.
Yes.
Actually, for each of the cities, the data comes from different sources. The case of Brazil, for example, in Salvador, the data comes from the census from IBGE. In the case of Nairobi, that is the most accurate data that we have because those data were produced with field campaigns from previous PhD students and previous researchers. From Mexico is also from their census, and also Medellin. It was also data provided by our partners there. And what we did is we got those data and we did, as I showed you in the data portal, in our data portal, we share the data that we have and the current predictions, and our users go there on new polygons, correct the data for us. So it's a mix of data from census, from previous researches, and also from our interactions with the users.
Okay. Uh, Hector asked, I'm curious about the validation process. He sent this message some minutes ago. Normally, when an inconsistent result is achieved, like a garimpo detect inside a conservation unit, it is set as false positive. Can you tell us about the challenge of validating the results in so poor original data quality?
No, actually, this validation actually took several months because, as I told you, in this one, because we know how complex the topic is, and we know how much attention this topic has. And because of that, we knew that our maps would would be prone to a lot of criticism and attacks. Then the guys from Solvid, especially Luis and Cesar, they generated, as I showed you here, they generated a grid of in the whole Brazil of 250 kilometers by 250 kilometers. And there we selected points equally distributed in both classes, mining and not mining. And with that, we brought all those 52,000 points for we evaluated 9 years on all those years that we mapped, and we brought that to experts in the field to validate one by one. So in most of the case, but like we can say that more than 90%, I think more than 95% of the garimpos that we found, they were real positives. And the point is, when they were inside a protected area, it's not that they were false positives. It's because they were quite likely illegal, like 99% likely
Mhm.
illegal. So I think though that is one of the when it comes to the intersection with the that is this slide here. No, this one when it comes to the intersection with the protected units, it's because it's quite likely that those garimpos they are illegal.
Mhm. Yes. Yeah, we have other questions. Christian Octavio said, excellent reflections on themes raised. We greet you from Chile, working in Latin America, Africa, and Europe. Yes, we have a lot of questions, but I don't think we can extend too much. But
Sorry that I extended too much the presentation.
no, no, it was perfect. You had so much to show. Now I understand when in the beginning of the presentation you said, "Oh, it's difficult to define which that case should I show because you have so much to show." Actually, this is a field with great potential, and you cover like theoretical aspects and like the applications they are different but they are interconnected, uh, and so it was great. Renzo
Thank you.
Larenas asked, do you have LinkedIn so I can follow you and learn about
Yes.
other talks similar? We can like schedule a second webinar again.
No, that would be great. I would be more than happy to present again. Just like on LinkedIn, I have not been so active there, but now I'm trying to come back and start being a bit more active there. But I'm there. Feel free to add
Okay.
me there, anyone that is
Yeah.
interested.
Yeah, so maybe they can like look for you there. Excellent presentation. Really interested and complete. A little fast, yes, because he had too much to show. But Ryan, thank you very much. Um, it was a pleasure to receive you here, and I hope we can like keep up with the connection and with the partnership. Uh, from the regional hub in Brazil. Thank you very much.
Thank you very much. Yeah, I hope we can find some of these topics to collaborate. We have had quite a lot of collaborations with Brazil specifically. It's one of our focus point here in ITC. And yeah, we are trying to stay in contact with as much institutions in Brazil as possible, but not only in Brazil, also in the whole South America, Latin America actually. And yeah, I hope we can have much more collaborations. If anyone is interested in the papers and couldn't get them from the presentation, I can share the papers later. The slides, several of these slides I got from our partners, so I would need to check with them if it is okay to share. Um,
Yes, but
but
it's
yeah,
great. Actually, we have a recording of the webinar, and it will soon be available on the website, so they can like go back to the video. It's great.
okay, yeah, and thanks again for the invitation. It was a great pleasure to spend this time here with you.
Okay, thank you, Ryan. I'd also like to extend a heartfelt thank you to all the participants and to the ECLAC Knowledge Transfer Network for providing the Zoom platform for today's event. And we invite everyone to join our next webinar on the Climate Change Indicator series, which will happen on March 19th. And it will be conducted in Spanish. So thank you once again, and we'll look forward to seeing you next time. Bye-bye. Thank you.
Thank you very much, everyone.